Everybody who's interested in this is here. Oh, well, I mean, this works. Do you want to wait a minute or two or?
Evan might show up late.
Okay,
Yeah.
you want to just go ahead and go? Okay, well, cool. Well, this is gonna be really informal then, which makes me very happy. So I'm not gonna introduce myself. Oh, maybe, I don't know if we've met. I'm Kelsey. I'm a new assistant research professor that got hired here with you and Douglas's group working on the Space Telescope project. But I was actually a grad student here many years ago as well. And I did my PhD over in OpSci, but all my work was over here in Steward. So I did astronomical AO. So I liked optics, but only if it pertained to telescopes. Otherwise, I did not care. So that's how I ended up over here. And so Ewan and Yuchia roped me into this talk very, very swiftly. So today I'm going to be showing you a whole bunch of charts from mostly my dissertation defense, old talks and some papers that I had to pull out of Relief to get the figures from. Everything you will see today is at the youngest information or newest information is 5 years old, and it goes even further back than that. But today I'm going to be talking about the work that I did for my doctorate, or a portion of the work I did for my doctorate, and then continued on during my postdoc. So I developed an algorithm and deployed it called linear dark field control, which we're just going to call LDFC from now on. And it's an algorithm that we designed such that we could maintain high contrast achieved either with a coronagraph or methods like EFC for exoplanet detection and characterization. So a little intro into LDFC, starting with what it is and what it isn't, because this is one of the common confusion, or at least it was 5 years ago. Maybe people know better now. What it is not is a method for digging a high contrast dark zone or dark hole. I'll use them both interchangeably because I don't know what people like to say now. So it does not dig a dark hole. It is not capable of that. That's not what it's designed to do. It is a method for maintaining the high contrast that already exists in a pre-generated dark hole, be it by, again, a coronagraph or methods like electric field conjugation. So EFC is a method for digging a dark hole. LDFC is then a method for maintaining that contrast. Another thing that has come to light since my glorious return to astronomy is that there are new versions of electric field conjugation like IEFC and ADEFC, which I am not an expert on. I am now reading Keon's paper on. So everything I talk about when I'd say EFC in this, it's talking about classic EFC, none of the fancy new versions that have come out since 2020. But this work was strongly motivated because prior to LDFC, EFC was a method that we used not just for digging a dark hole, but it was also one of the primary candidates for maintaining the high contrast within that dark hole. So constantly going back and basically redigging the dark hole whenever it degraded over time. And again, this is something, Keon, you're way more of an expert on than I am. I don't know if IEFC or ADEFC get around the problems I'm going to discuss here or not. That's something you and I will have to talk about at some point. But with classic EFC, if you're going to use it to maintain the dark hole high contrast, you basically are having to redo EFC and redig that dark hole every time. And EFC is computationally complex. It requires you building a Jacobian with a very precise optical model of your system. And then in order to actually derive an estimate of the electric field within the dark hole so that you can compensate for it, so you can get rid of the light, you have to apply probes. And so forgive me, this picture is like an image of an image of an image of an image. It was never a vector plot, so it's only degraded over time. But what you'll see on the top left is a terrible picture of an applied mode on a deformable mirror, and below it are the probes, the fields of the probes you would be applying using that DM. And then over on the far right, which you can see even less of, are images of those probes as they probe through the dark hole.
What is the mode on the DM?
It's a rect function.
Oh, okay.
Yeah, so that's a sync. ish. Oh, I will also say, since there is a lot of postdocs and graduate students in the room, nothing will haunt you like decisions you made in your early 20s. One of my choices was color map jet for everything. There are reasons to use it, and there are certainly times not to. One of the times not to is when most of your image is 0 and your main color is that heinous green. As previously stated, all this information is lost to the ethers. I couldn't have remade this if my life depended on it. So this is what we've got. But so anyways, if you can see in this very poor resolution image at the top right, as you apply probes in that dark zone area to estimate the field, to basically rederive the conjugate to get back to your initial dark hole high contrast state, you are throwing light back into the dark zone, which means that as an observer, if you are taking long observations in order to detect any photons from an exoplanet in that dark zone, which is the whole purpose of that dark hole in the first place, throwing light back in to probe the field and reinitialize EFC utterly destroys your observing run. So EFC, for that reason alone, was kind of a non-starter for maintaining the dark hole high contrast. Another secondary problem, but also a problem, is that it requires longer exposure times because there's not much light in that dark zone to begin with. And so you have to expose for a long time in order to back out an estimate of that field. So that's another issue. So it's not just, oh, a snap photo and we're back to our initial contrast. You break your observing run for a substantial amount of time. So this was what motivated the work to find a solution that would allow us to maintain the dark hole contrast, let's say after EFC or behind a coronagraph, or if you're key on both. And do it in such a way that you don't ruin long observation runs so that you can continue to collect light from a potential exoplanet. So this is why we developed LDFC. And so LDFC works differently. Instead of looking at the dark hole itself, it works by looking at the opposite side of the dark hole, which we'll call the bright field, because we're so cool at naming things, come up with great names. So the point is to stabilize the high contrast in the dark hole by instead looking at the bright field. And there's no Jacobian that's built, there's no optical model that's required. All that you're doing is you're building a control matrix that links your deformable mirror commands to your wavefront sensor, which in this case is your science image. And we'll talk more about that as well in a second. But it requires no probing. You can use a single image or, in reality, potentially a sum of a few images. And again, it uses the intensity variation in the bright field speckles to sense aberrations instead of the dark hole. And so you also can have much shorter observing times because there's a whole lot more light over on the left, especially, well, depending on the type of chronograph you're using, and certainly with EFC. But this is a good moment to pause and say, this is a very strange looking image. This is really weird. Anybody know what a VAPP chronograph is? Yes, no, kind of. It's fine to say no. Okay. It stands for vector apodizing faceplate. It's a pupil plane chronograph. It was developed by the guys out at Leiden University, which is why I ended up out there because I worked with them during my doctorate. We had a couple of these that we worked with in the lab. We had one on SCExAO and we had one designed for Mac AOX. So we're not going to go into how they work. That's outside the scope of what I agreed to talk about. But they use circular polarization. And they effectively are encoded pieces of liquid crystal that they do multiple things. You encode, basically, you would use EFC to determine what you would need to, say, put on a DM to dig a dark hole, but instead you encode it into these liquid crystal masks and it digs a dark hole. And then it creates two separate PSFs, one right circularly polarized, one left. And so you get two copies of your PSF. So you get a dark hole on the right and the top one, a dark hole on the left on the bottom one. And so the idea is that between the two, you have 360-degree coverage around your star. You then can also do really cool things, which was another part of my doctorate, but we're not going to talk about here. You can also encode a bunch of different sine waves at different frequencies and angles. And then with each of those sine waves, you can encode a mode. So these are Zernike-esque modes, actually orthonormal to our system. But these are basically low order Zernike modes, and we call this the holographic modal wavefront sensor. And you can watch those blink in and out. And as they increase in intensity, you can track that, and you can then, it basically becomes a physical linear decomposition of your aberration into these modes here. Cool stuff. Read my dissertation, or don't. I highly recommend you don't, and just come talk to me instead, but it's in there. That's why you see all this weird stuff in this image, but you're going to keep seeing this image throughout, and I just wanted to explain what you're looking at. So we're not going to look at the modes, the grid of modes in top right, bottom left. We're just going to be focusing on these two images here. So basic principles, how LDFC works. Keon's implemented it more recently than I have, so Keon, you just correct me when I say something wrong. So the idea here is that when you have an actuation or perturbation in your pupil field, and you look at the response of that perturbation in the dark hole, you end up with this quadratic response here, which anyone who's built a closed loop system knows this is not something you can build a control loop around. You will get nowhere very quickly. And so this is already problematic for if you're just looking at the intensity fluctuation, right? That's not the same with EFC. That's what you're looking at fields. Here you're looking at intensity fluctuations. This is what you'll see. We cannot build a closed loop control system around this anyway. However, if you make certain assumptions, you can in fact end up with a linear response. And so that assumption is that the bright field, your initial field, E naught, is going to be substantially larger than any field that's derived from the perturbations applied on a DM or atmospherically imparted. So what this reduces down to is effectively the intensity from your initial bright field is going to swamp the intensity variations that you'll see with any modulation in the pupil. And so the difference between a reference image I naught and an image at some later time post perturbation is going to have a linear response. And so when you in fact look at the same perturbations applied on the DM as we saw in the previous image that give us a quadratic response in intensity in the dark hole, we actually see a linear response in
What is
the
the amplitude of like the x-axis on the linear, semi-linear plot?
Oh, yeah.
Amplitude in nanometers?
So that is no. That's a pixel intensity response. So the poke amplitude applied is in nanometers down at the bottom. Is that you're talking about?
Yeah, is the poke like a one actuator poke?
Yeah, these.
Oh, okay.
Actuator. Yeah. Good question.
Yeah.
Yeah, go ahead.
Why can't you do control on the quadratic?
Oh, no, that's a great question. The reason is, let's say you have 100 nanometers of some aberration that you applied, right? And this is your response that you're looking at. If you have 100 nanometers of, say, coma that's been applied, and you measure 100 nanometers, well, it should be that, right? But it could also be negative 100 nanometers based on your response. Do you see?
Yeah.
So the problem is you lose sign information. You can't tell which way, you'll figure out the mode, but we don't have the luxury of the time to go, is it this one? No. Is it this one? Okay. So this is why you need at least a monotonic response. So it might have some fluctuation, but it's always going in the same direction. Because with the quadratic response, you're not gonna get the sign right. And when you're running at 3 kilohertz, you get the sign wrong once and you're dead. You're done. Your loop is open. There are caveats to that, but that's the idea.
Some noise can kick you back into a closed loop.
Yeah.
So.
Yeah, closed loops are fickle beasts.
Yeah.
But yeah, so that's a really good question. So that's why you want this linear or at the very least monotonic response, so that you can get not only the amplitude, but the sign of the amplitude correct. Because if you'll see here, it's going to be very different. Your pixel response is going to be very different, whether it's 150 nanometers or negative 100.
So you couldn't like take a 2 norm or something.
Yeah, it's you won't be able to back out which it was.
Do you have to control the pixels or can you control something like that?
So it's you're not actually controlling the pixels per se, you're actually controlling actuators on the DM. So the x-axis is the actuator poke on the DM, and the y-axis is an arbitrary intensity value pixel response.
It's like a movement.
That's right. Yeah. Oh, I'm sorry. Yeah. No, these are great questions.
I know nothing about this.
Great. Nice. Go away. Yeah. So yeah, deformable mirror has a bunch of actuators like fingers on the back that actuate at thousands of times a second. And so for these tests, what we did was just poke a single actuator up and down for these response curves. But you can also then make them all act together and form modes, which I'll also show pictures of here. So this linear response is the key to how LDFC works or why it can work. And then also there's the assumption of PSF symmetry between the dark zone and the bright field, the idea that that a perturbation will affect both the bright field and the dark field. Not necessarily in the exact same way, but you could still build a response, a control loop around the response of the bright field, and it will be related to what's going on in the dark field as well. And so now, maybe this is useful to you. Everyone else in this room has probably seen it, so that means I'm really excited if this is new to you. I'm pretty sure this is from Boston Micro Machines from ages ago. This is a basic diagram of an AO system where you have an inbound source, it hits your deformable mirror, and then you have some sort of beam splitting method. But the point is that you then have two diverging paths from the same source. One goes to your science image. That's what you're going to be doing all of your science with. That's where all of your raw data is coming from. And then you have part of that light that gets split off to a wavefront sensor, and that's what you're using to do active correction so that you get a good science image. And the problem with that is that with high contrast imaging systems, unfortunately, this method isn't good enough. So you end up with something that you'll hear people call NCPA, non-common path aberrations, which just means that there is some amount of optics and arms, relay arms between the wavefront sensor and the science image that are not the same, right? Because there's an optical path here and there's an optical path here, and there's air there, right? So there's things that are happening into the science arm that the wavefront sensor doesn't see. There's stuff happening in the wavefront sensor arm that it's going to correct for that's not actually happening in the science arm. And so you end up with these quasi-static speckles thanks to this NCPA. That we try to get around. So this method, to be clear, is not used alone. The assumption with LDFC is that it's a secondary wavefront sensor that's going to be running behind a primary wavefront sensor, like a pyramid, like for MAG-AOX. So the idea is that the primary AO system is going to be actively running and maintaining high strahl. So you're going to have a nice point spread function, high strahl, and that's going to be for the star and any potential exoplanet light. The point of LDFC is specifically just to maintain the contrast. It gives, oh, I shouldn't swear on this. It has nothing to do with maintaining high strahl. And so.
Neither does EFC.
No, neither does EFC. No, I just mean that it is a secondary wavefront sensing method. At no point is LDFC trying to actively control like high amplitude changes in order to maintain strahl. It's just looking at dark hole contrast. And so we get around the issue of non-common path aberrations by, instead of using a secondary path for the primary wavefront sensor, we actually end up using the science image as our wavefront sensor. And so that's, again, why we are interested in using LDFC, because it actually uses the bright field that's already in our science image, post-coronagraph or post-DFC. And so for LDFC, again, you see this very strange image given to us by the vector apodizing faceplate, the APP coronagraph. And so step one is to select the bright field pixel map that we're going to be using for our wavefront sensor to create our control matrix. It's a little more complicated than this. for this talk, I'm not going into it. So it has a natural outer bound, be it either the outer working angle of your coronagraph or the control radius of your deformable mirror. There's no reason to sense anything outside of the region in which you could correct. So it has a natural outer working angle. The inner working angle, it's a bit futzy. Sometimes we've used the core in simulation. That works really well. In practice, oftentimes the core saturates in order to get enough light in those higher spatial frequency regions. So while I show using the core here, oftentimes we did not include that in our control matrix, because by the time we had enough light from the higher spatial frequencies, the core was saturated and it was no good, no use to us. But so we select a bright field pixel map for our control matrix.
Can I ask a
Yeah,
question about
of
that?
course.
So if you're taking, I don't know how EFC works like at all. I have some general science idea of it, but.
Do you want me to go back to that utter garbage, low resolution picture?
But my general thing is that you basically have two PSFs
Yeah.
that are polarized, and you can use them to propagate each other, and that's how you dig the dark hole. So in the image there where you have like the bright mask, it looks like your PSF is almost like entirely in the right region, like see the core is like entirely in the right region. And I would just naively expect it to be like half cut off.
Sure, no, that's very understandable. So this is a pretty standard look for a dark hole derived with multiple different chronographic architectures like a VAPP. So let me back up. With EFC, you can pick whatever region you want. It becomes more challenging to do EFC close to the core, because when you run it, the solution it comes up with quite often is just tilt it, shift the PSF core off, and you have to go, no. I wanted like an inner working angle effect of like, 2 lambda over D. So you have to put in some constraints there, and you end up with some wonky shapes like this. But again, with this work, this was not EFC driven at all. This is just with a coronagraph mask in. And then, like I said, with Keon's setup, what they're doing on Scoob right now, they actually do both. They have a different type of coronagraph, which gives you a very different image than this. And then they do EFC behind that. So there's lots of different coronagraph architectures. They're not all going to look like this. In fact, most of them aren't. This is a very strange one in that it gives you 2 copies of your PSF with a dark hole on either side. Usually, you're just going to see one of those. So that's another reason why this work is kind of strange. Because we ended up using 2 bright fields to correct for 2 dark holes. And while we're talking about it, since no one else is online and I'm just with you cool kids, we thought, hey, dark hole, bright field. Done. We know what's going to happen between these 2, right? These are going to be very clearly linked, right? No, unfortunately, in theory, that would work great. But there are mechanical issues, and at the end of the day, the mask that you put in, there are some subtle differences, especially given polarization changes that might happen through your optical system. So when you end up splitting them and you get a right circular polarization PSF and a left circular polarization PSF, they are not the same. And so we tried doing control loops with just 1 bright field to correct 1 dark field. And it did end up cleaning up that dark hole to some extent. But if we wanted to clean up both, we had to use both bright fields. So they didn't fight each other, because that was another concern we had. They were similar enough. But if you controlled just 1 bright field, it didn't just clean up both dark zones, which was an unfortunate find for us, because then it became a little more computationally expensive. Well, twice, right? Because we had to use both. Not that it was too much already, but that was an interesting finding from this work. So normally you only have 1 bright field, 1 dark zone. But with this coronagraph, we had 2. And I tell you this just so when you see this in the future, you don't go, where's the other PSF? Kelsey said, this is just one particular instance.
Okay, I actually have a different question about a VF.
Yeah.
So what does the PSF of an exoplanet end up looking like?
Exactly the same.
that, it's a pupil plane coronagraph, so that's what I was
Yeah,
wondering.
it looks exactly the same.
Let's
Yeah, let's go. Let's go all the way back. Can you see it there?
Oh, they're on the right.
I mean, it's very bright for an exoplanet.
Yeah,
But yeah, so you can see it typically has its own dark zone too,
yeah,
right?
Yeah.
But that dark zone is gonna be so below the noise floor, you'll never see it. But so you get the same PSF structure, so it is strange. But again, if you have like a pyramid wavefront sensor running, and you're maintaining high strel here, you will have
Maintain
high
high
strel here.
yeah.
No, that's a good question, yeah.
That's an exotic PSF. to
It is
have.
an exotic PSF, it is super funky.
So is that you can see, that's what coming in the bright.
Yeah, that's a good question. So the idea, that's a great question. So, let me get back to where we were. If there is an exoplanet in this system that we're actually looking at, we've done our job well enough, we can see it. And it's over here, then it will also be over here, right? We will not be able to see over here because it will be so many magnitudes below the bright field here. It doesn't really affect us. We did some simulation work where we have an exoplanet in the bright field when we initialize LDFC, and it doesn't really end up affecting us much. And what the planets we were injecting were a lot brighter than we could ever possibly hope for. But that's a good question. That isn't a complete non-issue. I have slides for that in my defense. If you're ever interested, we can talk about that. But yeah, if it's in this dark zone for this coronagraph, then it would be in this bright field. And vice versa. But yeah, you absolutely, by eye at least, you will not see it at all. Okay. So now that we know a little bit about what LDFC is and we pick the regions that we're going to use to build a control matrix around. Now we build that control matrix. And so we have a series of modes that, again, I won't talk about how we derived in detail, but if you want to talk about it, I'm always happy to. We called them eigenmodes. Maybe now they have a smart name. We wanted modes that were orthogonal to our system. So what we did was we applied Hadamard modes onto our deformable mirror, took the SVD of those Hadamard modes, and what we ended up with was a modal-based set that increased in spatial frequency as you went up in mode order. So the first like 20 looked very Zernike-esque, and then if you go up in mode order with Zernikes, you basically get fancy scalloping around the edges of the pupil the higher you go. Those aren't particularly useful. We didn't want to do Fourier modes because we found that that didn't work exceptionally well for this. So we used these Hadamard modes to derive these modal basis sets that gave us a range of spatial frequency content and that were orthogonal to our system. And we called them eigenmodes. And I don't know if there's a smarter, better name for it than that now. But so I'll show you the first 9, and you'll notice they look very Zernike-esque. You'll see the deformable mirror up there change up top left, and then I selected a single PSF. So you won't be seeing 2 here, but you'll be looking at just 1 PSF here. So we apply the modes to the DM and we register the response in the focal plane. Again, looking at 1 of the PSFs, not 2 here. And what you're seeing here is the difference between the perturbed PSF and a reference image PSF. And again, like I said, we often didn't use the core because it was so saturated. And you can see that I've blocked the core here. So this is an example of some of the modes that we built.
What DM were you using for this?
So this one was the Kilo DM, the BMC 1K in the lab.
Yeah, same one we got.
So this talk is full of lots of fun surprises and semi-lies. There is lab results in here, there are simulation results, and then there are on-sky results, which are also a little bit of a lie, and I'm gonna tell you why at each step. So this was on the test bed here at the UA Wave Control Lab, which became the MagAOX lab. For reasons I no longer remember, that's a 32 by 32 DM. we only had, our beam footprint only illuminated 20 actuators across, so we weren't making use of the full DM. Hell, if I remember why that was the case for this setup, but that's what we had. And that'll come into play in a minute. But so we actuate the DM, we end up with our response matrix here. Because we've selected our bright field, these are our bright pixels, we've masked the ones where we've saturated, and now we have this response matrix. So now we want to build the control matrix. So now we have this response matrix. And this is where having this modal basis set comes in handy. So we build the control matrix by inverting that response matrix. And so when you do the SVD, because we're doing a pseudo inversion here in order to get the control matrix, it's rolled up. Okay. You get your eigenmodes here. So I think most of us in this room have seen this, some of us haven't. When you take the SVD, often what you like to see is a curve that looks like this. Because what this tells you is, this is your mode number on the x-axis, and then for me, I like to normalize the singular values so they end up at 1 up here. What you like to see is something, a nice curve with like a knee, because at that knee, you'd like to cut it off and say all the modes below it, we're not going to use in the inversion. Unfortunately, reality doesn't often give you this, and we certainly never saw that when we were on Sky. So this is on Sky data, because I liked this plot better than anything I did years ago in simulation. So when you are inverting those response matrix, that response matrix to get your control matrix, this is what you end up seeing. And this is where you decide what modes are going to be used in that inversion process and which ones aren't. So for the on-sky work, we use Tikhonov regularization. I've used other methods as well. We never found that there was one that was better than the other. But the reason we do this, you think, well, we have all these modes, why don't we just want to invert all of them, right? We went through all the processes to building this response matrix. And it's because as you increase in spatial frequency, your modes started to look like this. So you started to get really fuzzy. This is just noise. When you invert noise like this, you get really ugly, meaningless spikes in your control matrix that do nothing for you. They just, you can't build a closed loop around that. It's garbage information. And so all of these modes here, we started seeing these types of modes. So we decided we would suppress those modes in the inversion. And then on top of that, we said, well, some modes are higher spatial frequency. They are still high spatial frequency, but they have some noise, but they're still high enough weighted that we want them in the inversion. And so you end up with modes like this here, where there's some noise, they're not quite as clean, but we still want them to be included in our control matrix because they still have a really high weighting here. And so with those modes, we didn't suppress them like we did with these, but we used a modal gain binning, if you're familiar with this. So again, what's nice about these modes is here you can see that as they increase in order, they increase in spatial frequency content. And so if you're looking at a PSF, that means that as the mode order increases, the region they control around the PSF moves further and further out. And so this gives us spatial frequency control. So we can modal bin so that we can say, well, we suppress these modes, we don't want them. But these guys, we think when we get a response from them, it's kind of right, but not entirely. And so that means we can say, well, whatever amplitude this comes up with, let's say I see 5 nanometers of coma, we go, do you? And we suppress it by multiplying it by a gain of like 0.1. So we say, I believe it's kind of there. Not all of it though, and this is common practice. So we have a selection of modes where we say it's important, it has a high ranking, it has a high singular value, but we think it has a little bit too much noise in it, so we're going to suppress it with a modal gain. And then we have our unsuppressed modes, which is this section here up to mode number probably maybe 200, maybe 200. And we say, we trust these are good, not noisy modes, we let those pass through. There are different ways of doing this. For For this work, I believe we gave these a gain of 1, this a gain of like 0.1, and then this we didn't pass. But you can also do gain vectors, so you can do step functions. These modes have a gain of 1, these have 0.1, these have 0.01, or you can have like a nice linear function, depending on the type of system and the type of work you're trying to do. You can vary that. So again, we tried different things, but I think for this work, it was more of a step function. So I know none of that's really exciting per se, but this is actually at the heart of getting LDFC to work. Where you apply these cutoffs strongly affects how well the algorithm's actually gonna work.
Question.
Yeah.
I mean, basically just about constructing these modes in the first place.
Yeah.
But you're applying the series of your Hadamard modified modes that you
That's
said
right.
to your DM
That's right.
with a plain wavefront incoming.
That's right.
That gives you the response
Mhm.
modes. So, and then you invert them to see what you wanna put in your.
Okay, this is a great question. Yeah, I didn't
Yes.
explain this well at all.
Are those plots intensity is like, wow, the related.
Yeah,
question.
these are intense.
Okay,
No one online can see us, but luckily it's just you and me online, so it's fine. So on your DM, you apply a Hadamard mode, which is, I don't know, right?
yeah.
Something crazy.
Do you know what Hadamard modes look like?
Yeah.
Okay, yeah.
Wikipedia certainly does, they can show you, but QR codes, picture QR code. Take a Fourier transform, you end up with, your crazy PSF response, all right, because we're using the PSF as our wavefront sensor. So you apply the Hadamard modes and you get, our Hadamard, and I'm pretty sure this is in one of the papers. So now you have the response to, Hadamard modes. Now you break this down with SVD. And the matrix that what comes out of this are the modes that we call the eigenmodes. And so the eigenmodes are the SVD of this response matrix. So this is a really good question because I didn't tell you this. So now you have these eigenmodes, which is what we're looking at here. Those are our eigenmodes.
So each eigenmode is effectively a vector in the modified Hadamard basis, which is like some way to get an orthogonal mode.
That's right.
In response space.
That's right.
Okay.
Correct. And so now you have these guys, and we do this again. Okay. So now these are orthogonal to our system, right? To our pupil, to any optics that are in the way. This is now this will work for us and no one else. So now we apply these on the DM. And now we get the response from our PSF, again, being our wavefront sensor. And then this becomes the response matrix that we end up inverting. So we only use Hadamard modes to build the eigenmodes. We don't use the Hadamard response matrix itself. We don't get a strong enough response from it. It's better than actuator pokes, most definitely. But also with the modes that we derive from this, again, we have increasing spatial frequency content with increasing mode number, and that gives us what we need in order to do modal gate binning.
I'll ask you more stuff after.
Sure.
Keep going.
What I'll say is, let's look at my paper, because I don't remember. But all of this is in at least one of the on-sky papers.
I think part of this is also, I haven't worked with DMs in the lab.
Right.
So like the actuator poking, what you actually control, what you get out is a little bit, I know
Sure.
from theory, not from experience.
Absolutely. No, all of this is linear. Oh, you can't even see that pen from over here. I'm sorry. Oh, I chose that ugly green, just like the 0 point color map jet. I'm sorry, guys. Yeah, we'll look at it. It's all linear algebra. It makes more sense when you're looking at the inner dimensions of all of your matrices and you go, oh, it makes more sense. But we can talk about that later too. So now we're back to really beautiful, ugly pictures. And so this is all simulation work. So again, we have an inbound aberrated wavefront. Our deformal mirror is not doing anything yet. And we end up with this science image with, with these speckles. This is our aberrated dark hole minus the reference dark hole. So all that glorious green is a 0. And then all of the red and yellow, those are the speckles that have populated the dark hole based on the inbound aberration. So I've just highlighted them from that bottom image because they're easier to see. So then we have our bright field response. This is again, the modulated bright field minus your reference image. And you are able to derive your deformable mirror shape such that you are able to null those speckles. You still have residual aberrations in your wavefront that are beyond the control radius of your DM. Oh, I'm sorry. And so if you look at the images on the right, you see that we are able to drive those speckles out of the dark hole. And so that glorious green is your 0 point. I apologize for that. The red line, that is the control radius of our DM. It's about 10 lambda over D, because like I said, for some reason, we weren't fully illuminating the DM at the time, and we had about 20 actuators across. And so are you familiar with that relationship, the control radius and number of actuators on the DM? So if your DM, and like in this case, has 20 actuators across, so we're not talking about total, but just across the pupil. Think of putting a sine wave on it, how you do it. So column 1 would be +1, column 2 would be -1, column 0 would be +1, right?
Okay.
So you create a sine wave, all right? And that sine wave is then going to have a characteristic frequency that is half the number of actuators across the DM,
Yeah.
right? So if it had 20 actuators across, you can get a sine wave with 10 cycles across it, right? 10 cycles of +1, -1, +1, -1. All right, so when you take the Fourier transform of a circular pupil with the sine wave on it, what you end up with is copies at the characteristic frequency of that sine wave. So you get at half the intensity. So you get copies of your PSF at 10 lambda over D, because that's how we're measuring cycles then in the frequency plane. So if I only have 20 actuators across the DM, that means that the furthest it can throw any light is 10 lambda over D away from the core. So that's why you'll hear people say, yeah, it's nice it has 1,000 actuators, but what we really care about is, does it have 32 across? Does it have 34 across? Because that's what's going to give you that's going to define your control radius of your system. Outside that region, you can sense anything you want, but you can't control it. So why would you? So that gives you a natural cutoff for where you would, like for a focal plane wavefront sensor, what regions you would be looking at to control. Because it's silly to go past what your DM could do for you. And so, as you can see, because this was in simulation, but I modeled it so that it matched what we were going to have on the test bed. You can see that there's some speckles still further outside the control radius, but that was outside of our control bandwidth. So that was a lot of simulation work. We also did a lab demo. For those of you who work on Scoob, please don't laugh at us. This was your grandfather test bed or something. This was before MagAOX was even developed, or actually it was in conjunction with early development of MagAOX. This was our extreme wavefront control test bed. Really simple layout. We had a laser source that diverged. Oh, these are COTS OAPs, by the way, so garbage quality, not good. We had our OAP collimating. We had a reflective pupil that was supposed to look like MagAOX, or the Magellan telescope's pupils. We had another OAP relay here, which then created a re-imaged pupil size onto our deformable mirror, our Boston Micromachine's Kilo DM, at which point you'll see
That's a
Kelsey.
steep angle of incidence on the DM too.
Oh, it's not nearly as bad as it actually looks. This image really makes it look god-awful. It still wasn't great though. We had quite an elliptical pupil, to be honest. I think we were still about
MagAOX
10
is worse
degrees.
than this as well, but
I think we have it at 25 or something. Yeah. Certainly under 15. So it's not as bad as it looks, but you're right, it is quite steep. We had a very elliptical footprint on the DM. And so you have you want to laugh at the angle. Let me tell you something. We were trying to control the humidity in here because these babies don't like to run at above 30%. They will arc and fry between their little actuators. So we put this, we
Not
made this box.
immediately. Not immediately, like it happens over time.
It happens at a scale that makes you feel like it's safe and everything's okay, and then one day you're dead in the water. So we designed this box, it's a very pretty box, that we had dry air being pumped in constantly. And then we would turn it off when we would run, or at least we tried, because we didn't want to be adding more disturbances in there. So we had the DM, and then we thought, well, what good is it if we are pumping dry air in and we then have this window cut out in front of the DM? So what we did, which you can't really see here, is we had a thick wedge of glass window. It was optical quality, but we didn't want the beam going through this garbage plastic box. So we had a nice high quality optical window, but it was very thick, and we had to compensate for that because that shifted our pupil location drastically. This is on top of the window that we have on the DM already. Utter nightmare. Utter nightmare, but we made it work. So we had a singular DM relayed over here. We went from OAPs to lenses here because we ran out of money. And we were always monochromatic for these tests. We had a white light source, but we had filters in, so we were able to do laser line pickoffs. And so we did all this in the viz, because that's what these coronagraphs were designed for. And so we have a lens here. This is actually OAP4 and L1. These are a pupil plane relay. And so you end up with your pupil plane on this mask. Again, I actually have some really cool pictures of this we can talk about some other time, because we had several masks on here. This is our pupil plane coronagraph. Then we have another lens and a focus down to our science camera. So this was the extreme wavefront control lab back in the day. And so I have some lab results, again, in this garbage green, which I apologize for. So again, you see the control radius in red. That was the extent to which we could control the focal plane with our DM. In the bottom, and this is the video I'm going to run in a second. In the bottom left, we have our DM face. So we used our DM to induce aberrations and to correct. So you have multiple channels on your DM. So on one channel, we'd have the flat. On one channel, we would have the aberration we were applying. And on another channel, we would have the correction we were driving with LDFC. And so you sum them together, and you'll see what effectively you want to see is that the image on the bottom row, you want to see that go to 0 effectively. So left pupil image is the aberration, center pupil image is the DM correction being driven by LDFC, and then we had the residual phase in the far right pupil image. Up on the top, I selected the dark hole regions. So this is our upper dark hole, this is the lower one. The left side images are the open loop aberrated images. So I ran with just the aberration being applied on the DM, no correction. And then these were the closed loop results where it was the same correction or the same aberration being applied, but now with LDFC correction on top of it.
Is that a linear scale on the color bar, or is that?
No,
Okay.
it's not. This is, oh, I don't know if it's logarithmic. Well, it's not logarithmic. Maybe it is a linear scale. Actually, I think it is a linear scale. At least it is for the bottom one. So this is playing. So you can see, so you can look at both. So you can see, we still have noise in the pupil plane, but you can see we do a decent job of controlling at least the lower order modes in our DM correction. And so you can see we still have some low amplitude speckles that sneak in and out. But you can see that these are slowly evolving over here. You can see that as in these open loop images, as they slowly evolve, LDFC is able to keep up and keep these speckles out of our image. The lab at the time, specifically because of the optical quality and because of what the VAPP chronograph could achieve, our dark holes were like 10 to the -4 on a good day. That was what the VAPP could do. And then you added our optical quality garbage on top of it. And we were between 10 to the -3.5, 10 to the -4. So we were only, we injected speckles at about 10 to the -2-ish. And so at the end of the day, we were at best getting 2 magnitudes of correction. because that was the best we could do with what we had at the time.
But that's 2 magnitudes in the dark hole.
Yeah, in the dark hole, yeah.
Yeah.
So we were able to suppress speckles at least back to.
For context,
that level.
Sub starts at a 10⁻⁶ dark hole.
Yeah.
Just with the DM flat and the VVC.
So very, very different coronagraph architectures between the two. Because the VVC also is a focal plane coronagraph, which is gonna act very differently, and this is a pupil plane coronagraph. So there's just a lot of differences between them. And so this is what this technology could achieve. This was in their early days too, building these, and then our optical quality was just not great.
Your aberrated pupil phase, what you're giving, it's after AO correction, whatever residual is there, right? Or that's not
So-
just atmosphere.
So this one is atmosphere. This
Oh,
is the evolving aberration that we're applying.
okay.
This is the correction that we are deriving. Or I can't remember if it's the correction or if it's the estimate, Tracy.
It looks like the correction.
It's the correction, yeah. So what the DM is doing is this is on one channel, this is on another, because we didn't have 2 DMs, one to do the aberration and one to do the correction. So the best we could do is separate the DM into different channels. So we wrote this to one channel, wrote this to the other channel. This is the sum of the two. So you can still see that we don't drive perfectly back to 0. There's plenty of noise, but it's high spatial frequency noise. And so we still do a pretty decent job of cleaning up the speckles in this area here. And it's also pretty low amplitude, so low amplitude for what we were doing, and you would see this in Scream a lot worse than we saw it on our test.
Yeah,
bed.
like 5
Because-
nanometers isn't very noticeable at 10⁻⁵ contrast, but 5 nanometers at 10⁻⁸
Yeah,
destroys your dark hole.
100%.
So,
So this.
But also on Scoob, you don't have atmosphere, like even induced atmospheric effects.
no,
Yeah, so this is the best we could do back in the day.
Is like the fact that you're pumping dry air in the vicinity of the DM?
Oh, that would absolutely add. So we would pump as long as we could, and then when we ran, we would shut it off.
Okay.
And then, because the idea was you'd go and you'd turn it on and you'd get it as low as you could. We built a hygrometer that we put right next to it. We had constant, like, every second readouts, so
Okay.
we could monitor it. Unfortunately, we didn't have like an interlock system shut down, but we were able to monitor it. Because yes, that just pushing dry air and there would absolutely be a major source of aberrations for us. And so now, yeah, I know this doesn't make any sense. I didn't like to measure just the dark hole contrast across the entire dark hole. I liked to look at it in bands because it helped me understand better how our modal decomposition was working and our modal gain binning and seeing, how we were doing at different spatial frequencies throughout the dark hole. And so I did 1 lambda over D bins like this, semicircle bins. And that's what you'll see with most of my plots. So this is what I wanted to see in your paper or in your work that we talked about in the research meeting the other day. Don't use this color map and be smarter than I was. So this is looking at the average contrast in each of these different bins. We have 3 different colors to look at here. Hopefully no one's colorblind. You can all see the differences. Okay. That's another reason to not do it like this. So we had the average ideal dark hole contrast here. And this was mistake number 1 because it makes these results look worse than they are. I should have done the average dark hole contrast by bin since these other plots on each figure are by bin. Because the dark hole was not the same contrast across the full extent of it. And I corrected that in later plots. But so this is an open loop in the red. This is what the dark hole contrast was in this bin with our open loop aberration applied. And then the green is LDFC. When it was applied, this was our closed loop control, our closed loop contrast. And then I've dotted the lines to show the average. So you can see that we drive back to the dark hole floor here. What these plots don't actually tell you, but was actually true, is that they also drove back to the dark hole floor here. It's just that the dark hole was not as dark, the contrast wasn't as deep as you moved out into the dark hole. So this actually looks like we didn't hit it, but we actually did. I fixed this in later plots. This was a disaster. I should have done this differently. But this shows at least that LDFC clearly buys you at least a magnitude in each of these plots, in each of these different bins, and is driving you back towards that ideal dark hole contrast. So that was the end of my doctoral work. They finally, even with those ugly ass plots, let me go. Basically because they never wanted to see that color green again, and they knew if I stuck around, they would. So they let me out. I went over to Leiden, which is where they were developing those VAPP coronagraphs, and I worked with them. And one of the cool things that you all know if you work on Scoob is that you are able to log in remotely and work and use it, right? So even though I clearly have no idea what I'm doing yet on Scoob, I've done this before, that architecture came from AO, which came from SCExAO. And so we then deployed LDFC on SCExAO. And the cool thing about doing that from the Netherlands is it's exactly 12 hours apart. So you just log in at lunch and you have a beautiful night sky, and it was quite nice. So this work I did with, he was a PhD student at the time. He is now Dr. Steven Bos, a brilliant young man who I had the pleasure of working with in Leiden. He worked with me to deploy this work on SCExAO. And so since this is the end of the talk, I'm just going to throw pretty pictures at you from my papers. So on SCExAO, I initially had this say on sky. That's kind of a lie. Call it telescope demonstration because on SCExAO, they have an internal laser source, and that's actually what we used instead of Starlight. And they have a DM. I think that one was a 2K DM. They might have upgraded since. And so we used their DM like we had in the lab. It was our aberration source as well as our correction source, and we had an internal laser. And so we did the same thing where we applied aberrations on our DM, and we got results in open loop, so saw those speckles form. And then we turned on LDFC, and we closed the loop with LDFC. And all those plots with those modes, where we stopped for a minute and talked about the modes and the SVD and all, those were results from on Sky work. So that was actually from our run on SCExAO. And so this image is fine, but I didn't think it showed what we really wanted to see. So I did a reference subtraction. And so now you're left with just the speckles. So you have to remember where the dark holes are. So this is the dark hole region on each of these. And you can see you have speckles in the bright fields as well, because that's the signal you're using for LDFC. And then you have these regions that are your dark holes that SCExAO's VAPP was digging. So SCExAO also, their chronograph also only got down to about 10 to the -4th. And on Sky, that makes a little more sense, but we weren't on Sky. Technically, we were on laser on telescope. But so here with the reference subtracted, so this is open loop, an average of 1,000 images. This is closed loop average of 1,000 images. You can see that our dark holes here are once again quite dark. And we were able to drive back to, according to this terrible color scale, past 10 to the -4th.
Yeah, so what this is showing is just that the speckles in the dark hole remained the same throughout this.
Yep, so well, they remain the same kind of. We're actually driving them out. So what happens is, I mean, you start out here with these speckles, and LDFC is able to null them. That's not the right way. That's not the right way to put it. We're able to get rid of them. And then we're able to maintain that throughout a long observation. Did I answer your question?
Well, I was just thinking, like, if you go to 10 to the minus, if you make the color scale 10 to the -7, you would see that there are still speckles in the dark hole. It's just that they are remaining the same. So when you do reference subtraction, they go away.
Not for this. Because we hit the noise floor. So if there are speckles there, they weren't seen by our detector.
Yeah.
So So this is a better image. This also, I have other images in the papers that I list at the end where we increased the log scale stretch so that you can see a little more. These were just some of the ones that we had used in presentations. But yeah, so we freeze the state effectively of the dark hole. And Sanchi, you had a question?
Yeah, I heard when you say open or closed loop, you mean the LDFC?
Yes, sir.
loop.
Yeah. So if it's open loop, that means we were just applying the aberration and doing nothing about it. We just wanted to see what it would look like if we did nothing. And then closed loop was with LDFC turned on
But
and
it's still
actively
a dark
correcting.
hole being dug in the open.
So the coronagraph is just a pupil plane optic that just takes light from one side and throws it to the other.
Okay.
So we're not actively digging anything like EFC does. You can think of these coronagraphs as you use an algorithm to dig a dark hole using EFC. And then normally for EFC, you apply that state to your DM and it creates the dark hole. But instead of applying it to the DM, they encoded this in a liquid crystal mask. So it can't update, it can't change. And when I say liquid crystal, it's not an LCD. It's not an SLM.
Yeah.
It's nothing that you can change.
Okay.
It's actually the
Just-
same thing we use for the VVC.
Yeah, it's encoded. So it's always there. It's just a mask, right? But it's a phase mask.
Okay.
So it's always doing something. It's always going to create a PSF that looks like that. But as soon as your wavefront goes to hell, your contrast that it's creating is just nothing, right?
Yeah.
So good question. And then if you weren't sick of my ugly plots yet, let's zoom in on one dark hole and let's look at those speckles. And so this stretches a little bit further towards, so now the threshold is like 10 to the -5. And so you can see, yeah, of course, there's still something in there, but we're definitely at the noise level of our detector. And again, for us, this was the best we could do with the tech we had at the time.
So if this was the on telescope contrast, then what was the on sky contrast?
We didn't get to go to on sky.
Oh.
COVID hit. And we couldn't go in, and you could run this from home, and we did. We actually wrote the papers during COVID, but we already had all the on-sky stuff. But you needed operators at the dome, right? We couldn't open the dome, so we had plans to write further papers where we actually went from laser to stellar source, and the world had other plans. And then I left the Netherlands and entered federal service, and I haven't thought about this since. So I don't know if anyone has tried on Sky. I don't know if anyone at Leiden, I think everyone.
I don't know if anyone's done broadband yet.
No, so that was another thing. Let me show you this and then it's done. This is the last slide. These are the plots again that you saw where I'm looking at different bands, 2 to 3 lambda over D, 3 to 4, and 4 to 5. And you will see we learned from our mistakes, and now our ideal expected contrast, we actually we logged what it was in each individual bin. So you can actually see that this was the open loop, this was just the aberration, this was the contrast that we were going to have if we did nothing about it. And then you can see the green triangles. This is our LDFC contrast. You can see that we were able to come back down to the contrast floor that we were expecting. That was the best we could do on the telescope with that VAPP. So we were successful on telescope. We were very happy about that. There were still a lot of knobs we wanted to tweak. Like I said, if we go back to the modes we're using, the SVD decomposition and the modal gain binning, there's so many knobs to turn on this algorithm that are going to be very specific to the coronagraph that you're using, the DM that you have, and honestly, also your atmospheric conditions. So there was a lot of work to still be done when I left, but you do have to move on with your life at some point. So if I haven't bored you to death and I somehow piqued your interest and you actually care and you'd like to learn more, I was once an expert on this. And that woman wrote those papers. I am not necessarily the expert anymore. I have to go back and read my own papers. But if you also have any questions, can talk to me. My office is 580D. Sometimes I'm there, sometimes I'm not. That's my email. Miller K2. So I'm happy to talk about all this. I have tons more slides from the defense. I have the papers and the figures from the papers that we can talk about stuff. I'm especially interested to know how LDFC stacks up to newer EFC techniques like IEFC and ADEFC. That's outside of the scope of what we were going to talk about today because I don't know anything about them. But I'd be interested to see how it stacks up against those newer versions. Because I honestly really don't know. So thanks for all of you who came. This is really a nice small group and I actually really appreciate it. But if you have any questions, let me know now, right here. Yes, sir.
So I guess I'm kind of confused. You've never had more modes than you do the SVD, and then your end product is
more modes.
more modes.
It's another set of modes.
So,
But better modes.
Better modes.
yeah, so how are you determining the next control input from those modes?
So those,
Gain arbitrary?
so the gains. Arbitrary is not a terrible word for it.
That's not, it may.
Let's see. Okay, got this. This froze.
So it's like
So,
choosing the Tikhonov regularization
yeah, so
by eye.
it is, it really is. So maybe we can see this color better. So in the happy world, which is just simulation, when you do an SVD decomposition and these are your singular values, and this is your mode number, what you would love to see is something like this, where well, it's not supposed to curve out like that, it's supposed to curve like this. And I like to normalize it so the max one is just at 1. Just so it's not, just so then it's less arbitrary, right? You know, then it's always scaled from 1. So normally you look for this knee, and at that knee, you're like, this is garbage. We just don't need it. And then you can do like a linear gain function like this. But unfortunately, in the real world, you usually see something more like this, where there's no knee to speak of. And so with Theon, and so let's talk new fancy EFC sometime. Cool. Normally you end up with something like this, and it is definitively more arbitrary, which is why we even had these plots to begin with, was because we wanted to look at the modes and see how noisy they really were, because this was a weird shape, and we kept seeing it on sky, on telescope.
So is there like a control law, like an equation that you can say, like, I measure these modes, this is the equation I use to determine the new input that I give to my DM?
Yes. There are a few different ones, and different people use different ones. And I know even that answer is arbitrary. Tikhonov regularization is part of one of those methods, which is again, what we chose to do on Sky. But even that is, yeah, this is kind of arbitrary. Again, we usually go by the knee method, but if there's no knee, we ended up doing things like looking at the modes and seeing how noisy they were.
Also, like, having been doing a thesis, I kind of probably know more what you're getting at, because I think he worked on thermal control, and the thermal system.
I see what you're saying.
Part of the problem here is a lot of these modes are based, there's a mathematical set of modes, there's a real set of modes.
Yeah.
There's a DM that you can control that doesn't necessarily give you those modes. And you have to reproject bases.
Yeah.
And reconstruct bases of what is orthogonal from what you can control, and that is a lot of the game.
That is
correct. That's
correct.
where your driving kind of goes away from your control laws, because there's just noise that creeps into each of those steps.
Yeah, thank you. That's a really good way of putting
Yeah,
it.
I guess
Yeah.
I'm just trying to get it fit to what I do.
Yeah, and
I understand. I have also done that, yeah. Yeah, it sounds like you are a really good conduit for maybe this conversation, if you ever want to talk more.
I'm
about this kind of thing.
I had a similar question about, like, along those lines that I'm trying to clarify in my head.
Yeah. No, I love this.
Yes.
You're the professor now.
But like, basically, so you have a DM, which has a set of actuators. And they have their set of response functions, which will look like
True.
probably some subret or something. And yeah, and so when you construct your Hadamard modes, you're trying to construct a wavefront in your DM space, and then you basically say, well, what can my actuators actually make? Like, what shape can they make?
Yeah, so everything is always a projection onto your actuator space, which is basically a series of Gauss functions.
Yeah, and
So it's even weirder.
so when you're talking about those matrices there, and you convert to the modal bases, you went from this actuator space combination, you take SVD of this combo to get your eigen mode, which you said. Now you have a set of normal functions that are projected in your thing. And all of this is still a question, like if I'm saying something wrong. let me know.
No, you're nailing it.
Okay, and then you take so now you have normal modes
That's right.
that you can control
Yep.
that are like what you get on your detector.
Yes.
And now you take the SVD of this to get your, sorry, you invert this to get your response
Yeah.
matrix.
Yeah.
And that gives you, so this is where I don't. So if these modes are basically a series of vectors which are like actuator 1, actuator 2 apply this set of inputs to give this response. What is this inversion exactly? I don't understand.
Yeah, no, that's a good question, because there's one step that was missing, is that once you get these modes, you repeat the process. So these are already projected onto the DM,
Yeah,
but you now reapply them, and now you are looking at the response matrix is actually the application of those modes back onto the DM again. So they are in DM space,
okay,
because you projected the Hadamard's onto the DM, you did the SVD, you got the eigenmodes out. Now, we like those modes better than Hadamard modes because they make more sense, because they are orthogonal to our system.
okay,
And they do look like Zernike's, right? They're nice Zernike-esque modes in the low order modes, and they're ordered from low to high order.
okay.
And then as you go to higher spatial frequencies, they look more random, but they are now higher spatial frequency content modes. So if you're looking at your PSF,
Yeah.
as the mode order increases, you are controlling further and further out
Yeah.
into the dark hole.
Because the typical high order, for example, defocus will look like this, and then it'll
Yeah.
be just like a bunch of tiny circles
Yeah.
here, but in this space, it'll be like more evenly spaced spatial
Yeah.
frequency.
Yep, that's exactly right.
Okay,
Yeah,
Okay.
yeah, so yeah, you'd only miss one step there.
so this step is to go, just get the orthogonality and then just do the
Yes.
same thing.
And then you do it again, now you have your orthogonal modes, and now you're gonna build a response matrix.
So then this is, I'm guessing, and the reason why I'm asking all of this is
No.
I'm gonna work with, or to some extent, involved or interested in what Solvay is working on,
Yeah,
which is the
okay.
bending mode.
Thank you.
And so I'm guessing these are what they call bending modes now, which are the
Maybe,
Hadamard to normalized.
yeah, I've been watching that work on, like, it was the research group meetings and maybe somewhere else. And I've been trying to figure out what the
Yeah.
bending modes
Yeah,
work.
exactly.
And so, yeah. So I've had similar questions, but I haven't asked, because I don't like to put people on the spot when they really don't know me. And they just want to get through this meeting and be done, right?
I wish Solvay had with her, she has a class this quarter, this whole time.
Oh, that sucks.
If she was here, then that would be great, because then she
Yeah.
could look at your talk and then I could ask her this question.
Well, I can make these slides available. You all now know
Yeah.
where I kind of sometimes am, and you have my email. I'm happy to answer any questions, or we can reread my paper together and figure out what the hell I meant.
Okay,
Mm-hmm.
okay.
No, you might be the first person who's actually understood what the fuck I was saying, so thank you for walking through it. Cause it's not immediately straightforward why we do it that way.
No, the reason why I'm like really into this as well, just for my thesis work, I was doing PSF reconstruction
Oh,
and,
nice, okay.
but I had no classes. The only class they did was like just before I started working on it, and then
Yeah.
COVID happened. That class didn't happen.
Right, yeah, COVID really got in the way of a lot of
Yeah.
things.
So I had to like kind of learn a lot of this just reading papers, and so I'm also confused, but I also understand it.
Yeah, no, I get that. That's how I feel about, I think everything. At least the confused part. Some of it I also kind of get, but.
I get like a lot of when people are like, well, this is what you do and why you do it, the theory all makes sense, but like, how do you do it in the lab when you have this DM?
Mm-hmm,
That's
I
where
agree.
it gets me.
yeah, no, I very much understand. Yeah, happy to talk about
Like
it.
really like useful, and I
Oh, it makes me really happy to hear. Thank you. I hate giving pointless talks because I've done a lot of those too in my life, so.
I've also enjoyed HICE for that reason, because
Yeah.
I think through this year, I have just understood people doing a lot of dark hole digging, a
Yeah.
lot of like
Chronograph
Chronograph
stuff, yeah.
generally, yeah. Exoplanets as well. What were you saying, Amber?
I was gonna say, like, by pointless talks, did you mean like talking, like giving talks to like officers? And-
Yep. Yeah, I gave a lot of lab tours to people who they just wanted to see that, like, you know, science, engineering, you know, things are happening. Yeah, and I had to give those at all different levels too, because some of them had a little bit of knowledge, some of them had no clue. So, yeah. I mean, hopefully it kept the money flowing, but you know, it was not fun. They didn't know to ask these kinds of questions, you know, and that's not their fault. It's just like, you knew you were like the dog and pony show, right?
Yeah.
They were like, and look, she's doing science, and I could have been in there with beakers looking like Bill Nye the Science Guy, and they would have been like, yes, science.
Some of
So,
the LPs don't give a fuck, and then some of them like
and some give too many.
some of them want to know what's going on.
I had one lieutenant who he was really too gung ho, and we had to move an interferometer from one building to the other. And he almost just killed it. I was like, all right, let's do this. We'll unplug one cable at a time and make sure we know where everything goes. And the software wouldn't run unless you told it was 2007, the interferometers from the early 90s. And so it was just like this delicate beast. And he goes and he grabs a rolling cart and he just unplugs everything, he throws it on the cart, and then he's just gonna roll it across gravel to another building. I was like, stop. Just stop. And everyone else is like, what's wrong with her? Why is Dr. Miller screaming? Yeah.
Like, very, like,
But some were really great who did really good work, but a couple of them drove me up the wall. Yeah.
I was gonna say, it's like a very scientist in a movie moment where like they have no idea what they're doing completely wrong.
It's like, this is what it felt like at Jurassic Park. I know it. Oh, are we still recording?
Oh, yeah.
Oh, they're gonna get some interesting side stories.
Oh, yeah, you asked me. It has to be stopped from your.
Yeah.
Is it from mine?
No, from
Oh, okay.
And my computer is out of battery, so I'm bringing that to my office.
Oh, okay, no problem.
We can just leave the meeting.
Yeah, I think if you just leave the meeting, it'll
It'll just record.
Oh,
from
yeah.
Am I the only one?